So if you want to install this software, that is a DeepXDE, so I hope that you have already installed the Jupyter Notebook. So if you type Jupyter Notebook, so this session will be open like this, and you should create right click and you should run as a administration. That will going to open a terminal. Open the Jupyter Notebook, type here new, and this is going to open you one page, that is the notebook page. And here if you want to install the DeepXE, so you can use this command. Okay, so if you search in the terminal DeepXDE, okay, so it will going to show you this page. Okay, now here if you look for the installation, okay, so this documentation you can see here. If you want to visit, so you can see the documentation here, but currently I'm going to discuss about the installation. So you can see that there are multiple ways to given here to install DeepXDE. So you can copy this pip install DeepXDE and you can paste here. Okay, so and after that you can run, and you can see that I have installed this DeepXDE. Okay, now sometimes it might not work in case of you. So in that scenario, you have to put this symbol from your keyboard, and after that, if you run, it is so. To check that whether it is correctly installed in our system or not, if I run here import deepxd as a DD, so it should not show any error. It should correctly work. So it means that our system has installed the deepxd correctly. Now we are going to see the one conduction problem using the DeepXDE, and we are going to solve that problem using the PINNs. That is the physics informed neural network, and that is our first problem. I hope that you have already installed the DeepXDE in your system, and now we are going to solve your first problem, that is the one-day heat conduction problem using the PINNs, and for that purpose we are going to use the DeepXDE environment. So basically the problem setup is kind of going to look like one-day heat conduction equation, that is the del T upon del T, that is the time, and T is the temperature, and alpha into the del 2T upon del X square. So since we are solving one-day conduction problem, so the X we are taking within the range of the 0 to 1, and the time that we are taking within the 0 to 1. In case of our this problem, we are taking thermal diffusivity constant, that is equal to the around 0.4. Now, what is this thermal diffusivity concept? That if you solve the Laplacian form in OpenFOAM tutorials, then you should have aware about this thermal diffusivity constant. Okay, and still, if you are unaware of this constant, I would recommend to attend our CFD-ML workshop, where we are going to cover everything, even CFD from the basics and the machine learning concept from the basics. And in that tutorial, we are also going to cover this PINNs from introduction to the some project proposal that we are going to work on. So this is the thermal diffusivity. Now we are using the Dirichlet type of the boundary condition. And again, this is our initial condition, that we are using the sinusoidal kind of the boundary condition. So the sinusoidal kind of boundary condition is applied into the x direction, and this t is taken away as a 0. So that is why this is known as a initial boundary condition. So at a time equal to the 0, the sign type of boundary condition is applied, where temperature is varying with respect to the sign of the x, that is the x coordinate, and this is the exact solution. Okay, so if you solve this governing equation using this boundary condition and initial condition, so this is the kind of solution that you should get. So once after checking the applying the PINNs type of the solution, PINNs type of algorithm for the this only condition problem, we are going to compare this with the exact solution. So how we are getting the solution. So now what is the difference between the PINNs algorithm and other conventional method, that is the finite difference method or finite value method we used? So we generally discretize the different terms of the partial differential equation, and after discretization using either the finite difference method or finite element method or finite value method, we try to get a tolerance value that is provided by the user. Okay, so when this tolerance value matches, then we say that we arrived to the means accurate solution or near to the accurate solution. And what is the tolerance value? Tolerance is the means difference between the previous iteration value and to the current iteration value. So when the difference is less than the tolerance value provided by the user, then we say that we have arrived to the correct solution or some near approximate solution, we can say. But in pins, we generally optimize the loss function, which is means which is the kind of the loss due to the partial differential equation and loss due to the initial boundary condition and the boundary condition. Okay, so what is the loss? Loss is the nothing but the residual of the given condition. So in case of the partial differential equation, it is the residual of the partial differential equation, and this is the residual due to the inertial condition, which is a kind of the error between the initial boundary condition, and this is the boundary condition error. So we try to minimize this loss function. Okay, that is the idea behind the pins. Is this loss function, that is the total loss function, we are going to minimize. So as soon as we are going to minimize this loss function, we are approaching towards the approximate solution. Okay, so this is a some function that is means from the DeepXDE. Okay, so here we are creating the geometry. So this is the kind of the we are calling the DeepXDE module, and from that module we are creating this. We are taking some method, and we are creating means geometry between the 0 to 1. Similarly, we are creating the time domain between the 0 to 1. Now this is kind of a 2D kind of the geometry. So in one dimension we are taking this 1D direction, and second dimension we are taking a time domain. So that is going to kind of a 0 to 1 and 0 to 1. So one direction is the means x direction, x dimension, and another direction we are taking as a time domain. Okay, now we are going to define this partial differential equation. Okay, so here basically we are defining this du dt, and here we are defining the that Laplacian term. Okay, so what is the Jacobian and what is the Hessian function? So that for that purpose it will require means another video. So this is not something that I can explain in 2 or 3 minutes or some 5 minutes. So it is going to require kind of another session. So maybe I hope that you are going to join our session. In that session, we are going to see that how this Jacobian matrix and this Hessian matrix can be created for the this du dt and du double x. Okay, so once we define this transient term and this Cartesian terms, so we can now return our this partial differential equation. So this is kind of the partial differential equation. So if we bring this right side into the left side, so this is kind of the equation that we are going to get. Okay, so here we are putting input, that is the x, and second one is the t. Okay, now this is the initial condition that we are defining. Okay, so initial condition, as you see that we are defining this sinusoidal function. Okay, and this is the Dirichlet kind of the boundary condition that we are defining. Okay, so this functions, this different function, that is the Dirichlet BC and IC condition, that is kind of a function, or we can say the method is already coded into the DeepXDE. Okay, so what are the different terms that we need to call if we are going to use this Dirichlet boundary condition or Newman boundary condition or mixed kind of boundary condition, that we will look into the our complete session onto the pins. Okay, so again this is also a one method. So what are the different type of initial condition that you can define using the DeepXDE? Okay, so that we are going to see when you join our session on the CFD-ML. Okay, we are going to use the Adam optimizer first. Okay, and see that where we are getting the solution correctly or not. And after that, we are going to use the LBFGS optimizer. Okay. So in generally, if we solve a simple partial differential equation, in that scenario, this ADAM optimization is sufficient to get the good approximation of the solution. Okay. But in sometimes we need to get the precise fine tuning solution. So in that scenario, we generally use the LF BFGS. Okay, and also the solution we get using the ADAM optimization sometimes it requires further fine tuning. Okay, and after that we use the this LBFGS. So when the solution or model is the near to the convergence, okay, in that scenario we use the LBFGS optimizer because it leverages its ability to approximate the second order derivative efficiently. So that is the advantage of the LBFGS optimizer. And another advantage is that in ADAM optimizer we have a fixed number of iterations. But this optimization, that is the LBFGS optimization, it dynamically determines the convergence. Okay, so that is the difference that we can see between this ADAM and LBFGS optimization. Now after that, we will train the model. Okay, and we will see that how solution is compared with the exact solution. That is why I have given that what is the exact solution. So we are going to compare the solution between the exact and the this PINN solution. Okay, and this is the summary. Okay, so if we are using the DeepXDE, so this means package, that is a DeepXDE is mainly made up for the solving the PINNs algorithm. Okay, so this is the this package DeepXDE is the made by the one student of the George Kim Kardashian, who is the father of this physics informed neural network. And this is mainly act as a good framework for solving the partial differential equation using the PINNs kind of algorithm. Okay. So here we are going to see the coded part of this session. Okay. So we are going to see that how code has been done for solving the 1D conduction problem using the PINNs. Okay. So here we have imported a library. So this DeepXT you can import as a DD, and this NumPy, which is the one of the Python package which is used to means handle the data into the matrix form. Okay, so these things we are going to cover into the machine learning. So in machine learning, we are going to cover the Python part as well as the introduction to mathematics of the machine learning, as well as some package related to the machine learning. So these things we are going to learn in our machine learning session. And after that, we have created the data for the exact solution. So if you see my slide part, you can see that I said that we are going to compare the PIN solution with the solution got from the exact solution. Okay, so these things this is the way to means create the uh, exact solution. Okay, how we are doing this, these things is not much difficult thing. So everything, how you can define the function into the Python, and how you can create the your own means values from a given partial differential equation. So these things will be covered. Okay, so don't worry about these things at this level. Okay, now this is the variable, that is the a is the alpha, which is the thermal diffusivity. So L is the dimension. So we are taking in x direction is around 1 unit, and t we are taking around 1 unit as a time. Okay, okay. After that we have get the exact solution. Now these things I have covered. Okay, so here first we are creating the geometry domain, and after that we have created the time domain. Okay, so this geometry domain will be from 0 to L, and this is the time domain is from 0 to n. Okay, now this is geometric time domain we are creating from the geometric domain as well as from the time domain. So this is we complete the geometric time domain. Now we are defining the partial differential equation. Okay, so this Jacobian and Hessian we are going to cover in our PINNs module 4, which is the part of the CFD-ML global workshop. So we are going to cover these things, how you can define this Jacobian and Hessian function, And after that, we have created this partial differential equation. Okay. So, and this is the way of the creating the boundary condition and as well as the initial condition. Now, see, this is the data that we are creating using this partial differential equation and this boundary condition and initial condition. So, how much points we are taking? So, for the domain thing, we are taking around 2540 points. At the boundary, we are taking 80 points, and this initial boundary condition, we are taking around 160 points. So, these are the data is going to generate it using this PD and the boundary condition and initial condition. Okay, so this data will be randomly data, and it will create the values using this PD equation and this boundary condition and the initial condition. Okay, and as I told you that we are defining this fully neural network. So the input will be around 2 input, and then after that we are defining 20 neurons for 3 hidden layers. So this 3 means that we have 3 hidden layers, and this is around 20 neurons, and the output will be one neuron. That is the temperature. We want to solve these pins to predict the temperature. So that is why this output will be around one. This is the 3 hidden layers with each hidden has the 20 neurons, and the input is the 2. In our case, that is x and t. X means that geometric domain, and t is the time domain. Okay, so this for this hidden layers we are solving for around 20 neurons. Okay, it means that we are trying to predict the 20 weights, okay, at each neuron. Okay, so this is basically we are trying to solve. Okay, now this data that we have generated for this partial differential equation, so around 2450 for the domain, 80 for the boundary condition, 160 for the initial condition. That data is going to be input into the model, and this net, that is the neural network that we have created from using this FNN, that is the fully neural network. We are going to take input into this model, and okay, and this model is going to compile this data in the neural network using this ADAM optimizer and this learning rate. Okay. Now, as I told you that this ADAM generally takes the fixed number of iteration. So here we are taking around the 20,000 number of iteration, and we are going to train this model. And you can see that we are printing the loss history here. Okay. So if you train this model, so this is the uh, loss for the train model, and this is for the test model. Okay, so you can see that the loss is around 1 e to the power minus 6, which is we can say that basically in the acceptable range, and it will take around 80.087 seconds to train this model. Now, what is the test loss and what is the training loss? How much percentage should be there is a test data, and how much should be their trained data? So that will be covered during the our machine learning classes. Okay, so don't worry about this. These things basically basic things of the machine learning. So that is what is the 10H, what is the ADAM optimizer, okay, what is the how this fully neural network is being defined. This topic will be covered into our machine learning classes. Okay. Now, as I told you that there is a slightly difference between the ADAM optimizer and LBFGS optimizer. So here you have a number of iteration is fixed, but here the number of iteration is not fixed. It is dynamically determined by the optimizer, that is the LBFGS. Okay, so you can see that it will also training taking around 20,000 iteration, and approximately same train loss and test loss it is given here. Okay, so this is a simple problem, so that is why we are getting the approximately the same train loss and test loss. Okay, now the advantage is that it is taking a lesser time compared to the ADAM optimizer. Okay, so this two optimizer we will see details into the mathematics of the pins. Okay, so don't worry about at this point. So once this model is trained, we are going to compare the solution here. Okay, so first we are printing the train loss and test loss, and after that we are comparing the residual of this different data predicted by the PINS model. And you can see that this error is around 0.00188. Okay, and also L2 norms error is around 0.001. So these are the what is the L2 norm error and what is the main error. So these are the basic means the mathematics of the introduction to the machine learning. So we will cover this. Okay, but this norms that we are the error we are getting, we can say that the error is in the acceptable range, and this is just a simple model. Okay, so we will see other examples also during our session. So where we are also going to use the OpenFOAM data to train the PINS algorithm. So this last function that we have only three last function that we are seeing here. That is the means partial differential equation loss. Okay, boundary condition, initial condition loss. But we are also going to see that how this data loss can be also used as a residual for training the PINS algorithm. So these things we are going to cover into the our CFD ML global workshop. Okay, so though friends, this is just a basic example. I want to show that how you can solve one day problem using the PINS model. But if you want to learn more about this PINS CFD ML, so you should join our global CFD ML hands-on workshop, which is going to happen at online mode. And this is our team member. So I myself is going to cover the pins and some of the projects related to the same CFD. Abhishek and Govind and Srijna is going to cover the CFD and pins part also. Okay. For the machine learning part, I have this Suraj and Kundeswar Prabhu, who is the AI consultant at the Bharat Gen, so which is one of the government initiative. So they are leading that initiative as a consultant. So I thought that they will be better mentor for training the machine learning part. So that is why they are going to uh, cover this introduction to machine learning session. And if you want to see our orientation session, you can go to this QR link, and this there is around 1 hour orientation session related to this global workshop, and you can learn about how we are going to cover this course and what are the different session parts we are going to cover in this course. And now if you want to contact us, this is our contact numbers and contact Gmail. So I personally would prefer if you mail me on this given Gmail, but you can also text me on WhatsApp. This is WhatsApp number for iteraSim, and these are the different key concept is going to be covered here. So this is all about the workshop. So it is going to start from the 15th July. We are going to basically cover the CFD and machine learning. So generally we take classes on the Friday, Saturday, Sunday, around 3 hours, and it will be around 40 hours total, 40 hours of the live intersection session. But it is not the limited to this 40 hours. Our main part is to cover the content that we have said into the orientation session. Okay. Apart from this workshop, if you're registering for this course at this fee structure price, you are going to get this OpenFOAM 40 hours OpenFOAM programming training session. So remember that we are currently selling this course at the price of the 8,000. So if you want to someone take only courses on the OpenFOAM, advanced OpenFOAM hands-on programming session, so they have to pay 8,000 for this price. But if you are registering for this CFD-ML course, then you are going to get this bonus constant at the free of cost. This is the registration link, and the early bird price you are going to get only up to the 7th July. So please do register as soon as possible. And these are the some highlights that I can say that we are a first company who has organized so much of workshop at the top institute of the India. So we have conducted 3 times workshops into the IIT Bombay, and we have also conducted workshop at the FMFP, which is the one of the international workshop for the fluid mechanics and fluid power at the Nirma University. Okay, we also regularly upload our CFD content on our YouTube channel. So if you want to see our uh, review about our teaching skills and our contents, you can go to my YouTube channel and you can watch there that how we cover these things. Okay. Apart from this global workshop we have conducted last year, which is one of the most appreciated workshop. So many faculties from the IITs and NITs have appreciated this workshop, and they have bought our courses. Okay, so this is all from my side, and I have ending this session, hoping that you will soon register for this course, and we will again meet into the CFD ML Global Workshop on the 15th July. So thanks to a lot of you.